everybody. Let's do more dynamics problems showing kind of the difference between Newton's way and the work energy way. And let's do some examples using the Atwood's machine. That's the one if you have a pulley and then you suspend two masses. If you let these go from rest and the blocks are the same mass, nothing would happen. But then let's say M2 is more than M1, then M1 is going to go up and M2 is going to go down. And the acceleration is going to be less than g, depending on how much less depends on the ratio of these masses. So how would you solve for the acceleration? So you should draw the free body diagrams, right? So for block 1, there's the string, and then it has weight. For block 2, there's the string, so there's tension, and then there's weight. And you can pick coordinates however you want, like say like this. In this case, block 1 would accelerate in the positive y direction, block 2 would accelerate in the negative y direction. So for me personally, I know block 1's going up. So I'm just going to draw my coordinate x is going up, and I'll call it whatever I want, x. And then since I know block 2 is going down, I will also draw my coordinate axis in that direction. And I'm even going to call it the same x. So in this case, both blocks are moving in the positive x direction. That way I don't need to keep track of like which one is positive, which one is negative. They're both positive. Okay, so now Newton's laws, T, mass times acceleration for block 2. X is this way, right? So m2g minus t, mass times acceleration. And if we know both masses, so if we know both, the only unknowns, tension, acceleration, tension, acceleration. Two equations, two unknowns we can solve. So let's see, which way should we go? How about, let's solve this for t. And then put that there. Okay, so let me do that. Minus, I'm writing this equation, minus t equals m2ax, and then t was this. Okay, now we only have the one unknown. So let's solve for that. So I'll take this minus and move it on that side. And then we're left with m1 minus, oh no, m2 minus m1 over on this side m1 plus m2. And then I can take this and move it in the denominator. And then that's it. That's the acceleration. Okay. Now, what is the speed of the blocks? So block 1 has a velocity like this. Block 2 has a velocity like this. Let's say after it goes some distance d. How fast are they going? So to be very specific, they have different velocities because they're going in different directions. But the magnitude of the velocity, the speed, would be the same because they're connected by the same string. Okay, so how do you find the velocity? So notice that this acceleration is constant. So because it's constant, we can use kinematics for constant acceleration. So we can use the one that looks like this. And then if we start at rest, this is 0. This is the acceleration. It goes right there. And that was some distance d. So then this would be 2gd, that whole thing. And that's v squared, so square root. So this is the speed. Okay, let's do the same problem using WorkEnergy method. So same problem. This block goes up here. This block goes down here, some distance d. Okay. Their work by non-conservative forces plus initial equals final. There's no friction. Let's ignore the friction in the bearing of the pulley. Okay, 0. So energy is conserved. So these are at rest. So let's go one by one. Block 1 is at rest. So no kinetic energy. Block 2 is at rest. No kinetic energy. What about gravitational potential energy? Depends where we pick the datum. So for block 1, how about I pick the datum here? And then for block 2, just to change it up, how about I pick the datum here? So datum for block 1, datum for block 2. Okay, so for block 1, it's sitting at the datum initially, so the gravitational potential energy, 0. For block 2, it is above the datum, so it has above, so positive m2 g d. And then that's it. Okay, now final. Now we're here, so block 1 is moving with some speed, so it has kinetic energy. Block 2 is moving with some speed, so it also has kinetic energy, 1/2 mv squared. Okay, now gravitational potential energy. Block 1 was here, now it's up here. So it's above the datum, so plus m1g, the height above the datum. Block 2 was here, now it's here. So it's at the datum now. So now for block 2, the gravitational potential energy is 0. So then that's it, we're done. Let's solve for our unknown here. So I'll take this and move it on the other side. And then what can we factor here? 1/2 v squared. So I can take this and move it on that side. So I'll take the 2, put it here. And then this goes in the denominator, equals v squared. So there you go. So this is the speed. Let's compare it. Same. Okay. Let's have one more example. Let's mix it up a little bit. So how about more complicated? Like say there's a pulley here. Okay, so let's say there's block 1, and then there's a pulley connected to block 2 over here. And there's a spring, and we know the spring constant. And let's say there's friction over here, and we know the coefficient of kinetic friction. And this ramp is at some angle, and we know that angle. Okay, can you solve for the acceleration of the blocks? Can do, right? So for block 1, draw the free body diagram. There's normal force, friction, weight. If block 1 goes down the ramp, then the spring force is going to be opposing that displacement here, right? And then there's this cable this way, tension. Okay, so that's the free body diagram for block 1. And then for block 2, there's this string, and it has weight. Okay. And you can pick coordinates however you want, but here's my style. I know block 1 is going to slide this way, so I'm going to pick my coordinate that way. And I know block 2 is going to fall down. So see what I did? Both blocks are moving in the positive x direction. I'll pick y. And here we go. Okay, the angle's here. Let's write Newton's second law. Okay, so for block 1, x direction, we got, okay, and then minus friction. And I'm just going to write it right here. Friction is mu k times n, well, kinetic friction. Okay, and then minus spring force. And now spring force is proportional to the displacement. Now, which way is the displacement? X. So, X. Okay, and then there's the tension. Equals mass times acceleration. Okay, in the y direction, okay, equals mass times acceleration. And then for block 2, I'll just write it down over here where there's more space. So for block 2, mass times acceleration. Okay, also note that, see how block 1 is going this way in the x direction? There is no motion in the y direction, so the AY is 0. Okay, now let's see. What do we know and what do we not know? If we know all of these, then the only unknowns left: normal force, tension, let's see here, the acceleration, and the displacement. This is okay, so let's see. So strategically, this one has a lot of unknowns, so I'll substitute things into that equation. So for example, right here, I can solve this for n and put it here. I can solve this for t and put it here. So I'm going to do that. So I'm going to copy this equation, m1g sine theta minus mu k n, but look, n is m1g cosine theta. Okay, and then now here, minus kx plus t, but look, t equals m2g minus m2ax. I'm going to write that right now. Equals m1ax. Okay, so the unknowns. There we go. So I'll move this on that side. And then, let's see, we can factor a little bit. So I can combine these two. And there's also plus m2g. I can factor a g. Okay, and then minus kx equals m1 plus m2 ax, which I can move that in the denominator. And there's the acceleration. And note that the acceleration is not constant, it's a function of the displacement of the spring, right? Okay, and then how would you solve for the velocity? We did that earlier in another video. You would have to integrate this, right? Because now this acceleration is a function of x, see right here. And then you can't just go dv dt, because how do you integrate this dt? Right, so you can do this chain rule trick. Dv dt, and see how there's x. that's our intermediate variable, like this. So see that chain rule, dv dx, dx dt. But dx dt is v, right? The time derivative of position, velocity. So now this equals this, right? So it looks like, okay, let me just write it again. Okay, I take dx and move it on that side. That's separation of variables. And then on this side, and then we can integrate. So now we can integrate, look, over x. We can integrate this over x. And then you simplify, and then that's how you solve for v. So you have the speed. Okay, and then now, let me copy this. Okay, now let's do the work energy way to solve this. So work by non-conservative forces, initial, final. So the only non-conservative force doing work is friction. So what is the work by friction? Work by friction would be, the friction force is this way. The displacement is this way. So what happens when you dot these two vectors? It's a scalar, and these are 180 degrees. So it's this times this magnitude times this magnitude times cosine of the angle, which is 180. So it's minus this times this is the work by friction. Let's go into a little bit further detail. Friction is mu k times n. And let's recycle our work we did earlier when we did the free body diagram here. And we solved, see in the y direction, n minus mg cosine theta equals 0, which means n equals mg cosine theta. So let me write that over here. Minus mu k, n equals mg cosine theta. Okay, let me put the d over here. So there we go. This is the work by friction. This. Work by friction. Okay, let's finish the rest of it. So this block moves over here later and is going at some speed. This block is over here later, moving at some speed. And let's say this distance is d. Okay, so how much energy here? So if it starts at rest, the kinetic energy, 0. If the spring is unstretched, the spring potential energy, 0. Let's say the datum for block 1 is here. The datum for block 1. So then the gravitational potential energy is 0. And then let's say for block 2, how about I put the datum here? So it's also sitting at its datum, so the gravitational potential energy is 0. And so we're done here, that's 0. Okay, final. This block is moving with some speed, so it has kinetic energy, 1/2 mv squared. It is now below the datum. It used to be here, now it's down here. So it moved right from here, now it's over here, this far. What is this height that it changed? It's definitely below, so minus m1g times this. And so if this angle is theta, the triangle looks like this. So that would be d sine theta. Okay, and then the spring was unstretched, but now it got stretched by this much. So the spring has potential energy, 1/2 k, that much squared. See how it's positive? Because if you smash a spring or stretch a spring, you're squaring that number. So it's still going to be positive. Okay, and then for block 2, it was at the datum. Now it's below the datum. By how much? This much. So minus M2GD. And here we go. The only unknown we can solve for the speed. Oh, I forgot the kinetic energy for block 2. The block was at rest, now it has some speed. So plus 1/2 mv squared. Okay, so here we go. Solve for that speed. All right, just pick all this up, move it on the other side, times, and then you can factor 1/2 m1 plus m2 v squared equals all that rest of it times 2 over m1 plus m2 and then square root. Then you have the speed. Okay, so give this problem a try. Give all of these problems a try yourself for practice, and then let me know if you need help, and I'll see you on the next video.